Okay, today we're talking with Brighten Godfrey, who's a professor at University of Illinois, Urbana-Champaign, in the computer science department. He also has a startup, Veriflow Systems, that's in stealth mode. And we're going to talk today to Brighten about network verification. So he's done a lot of work in this area dating back many years, and we're going to learn about a little bit about both his research and what's the latest and greatest in network verification. So thanks, Brighten, for chatting today.
Sure. My pleasure. Thanks for the invitation to come chat.
Cool. So I think there's been a lot of interest in formal verification of networks. I think in SDNs in particular. It seems to be, at least in networking research, it's like kind of one of the hot topics, you might say, these days. Of course, debugging networks is nothing new, and operators have their favorite tools for doing this already. OpNet and various simulators and trial and error, I guess you might say. But I think in your research, certainly you've definitely thought about bringing formal techniques to bear for these kinds of problems. So I assume one of your goals is to kind of eventually bring these formal verification techniques to operation and practice. Can you talk just a little bit about how the techniques that how you came to start working on this problem and the techniques that you developed in your research, how those sort of apply to operations, and if and how those kinds of things are sort of making their way into practice?
Yeah, sure. So I think, this research goes back in our group to really around 2010, and of course we're building on work in the research community that's in the area of debugging and checking and verification of other parts of networks that dates back long before then. So I think the way we started looking at it was, how would you be able to provide an assurance on what's actually happening in the network? That is, how do you see, there's moving from some of the existing tools that are more simulation oriented, like let me simulate what's going to happen to this packet or that packet. How do you go from there to something that's really more like formal verification? That is, that explores all possible behaviors in a network and gives you a confident answer about what's really happening. So that was kind of the start of the philosophy, was to see as close as possible to what's really happening in the network, and that led to this approach. Which was the new aspect in our original work, was what we now call data plane verification, where we're picking out information that's close to what's, that's as close as possible to, the hardware instructions, basically, that control packet processing throughout the network. So that's where this kind of verification started. And I think what's new, what's exciting about it is that, as I said, it's verification. You can explore all possible behaviors. So it's this, there's an art to, I think, finding the right domain where you can actually do that, right? The idea of figuring out what software does goes back, many decades in computer science, but for general purpose software is a very complex system. So if you can find a domain like networking, like data flow within networking, where you really can actually, it's feasible to explore that behavior and get formal verification, that's an exciting thing. So I think in terms of how it becomes operationalized, that's something that we've been pushing on from the beginning. So and I should say that my comments here are in my role as a professor on our research side, since the startup is in stealth mode. And on the research side, for example, we worked with an operational network, did verification on the backbone, and this is the backbone of a network that's supporting around 100,000 machines. And we didn't really know what we'd find when we first started that, because I didn't have very much operational experience, right? Would you actually find problems in networks using these formal techniques? So there were in fact problems that we could pick out. Loop detection is maybe an easy one that comes to mind, but then you move on to properties like consistency checks and so on that can actually figure out real operational problems. So I think another good example of how this area of network verification moves towards operations is after some of the early research work on this technique of data plane verification, there's been some great work at Microsoft Research to operationalize it, and that includes work that was led by Nuno Lopez, published in NSDI just a few months ago, describing the systems they built, the data plane systems they've built, which are now in use or as described in use at Microsoft's Azure data centers.
Interesting. Actually, one of the things that you sort of talked about a little bit in just now was scaling and sort of I guess the difficulties that some of the other techniques, simulation and other sort of per packet kind of properties have as far as just scaling difficulties. And of course, some formal verification techniques also have scaling difficulty if they're exhaustive, right? But of course, there's been a lot of work trying to get those techniques to scale. Are you finding that things that people have done, tricks that the formal methods folks have discovered to get these techniques to scale are applying well in the networking setting?
I think some of them either apply or there are analogies. And then there are other areas where it's more network specific, right? So if you look at what we did in Veriflow, you can squint at it, and it's pretty similar to a kind of symbolic execution. And some of going back even further, actually where we started with the original work, which is this project called Anteater, before we moved on to the Veriflow research project, the earlier research project, Anteater, we actually started with SAT solvers, right? And we represented, there's actually some work there, and there's some earlier work than ours that was actually taking networks and representing it in terms of Boolean formulas, right? So it kind of there's early work that does that. That was work by Jeffrey Shea and Jen Rexford. I believe we're both on that work. And so in our Anteater work, we represented networks including packet forwarding and transformations to packets and how packets flow multi-hop through network, and thought about, okay, how do you code that into a SAT formula to check a property, right? Where satisfiability is this lower level representation of is a formula, a Boolean formula involving true and false values and constraints between them. Can it evaluate to true? So there's definitely concepts that transfer, and then there's other concepts that are pretty network specific. Like, for example, if you look at Veriflow, the basic computation in it is graph oriented, right? We have a topology of a network, and we're traversing this topology that in a way that understands what the network does. Interesting.
So I guess. With regard to that, are there certain there's certain types of properties that lend themselves pretty well to that kind of checking with SAT solvers? I think like some of your research work has focused on reachability properties of certain kinds. Maybe there are others as well that you wanted to mention, but I'm curious too, like as far as operationalizing some of these things, and you mentioned sort of trying these things on the operational network. Are there certain things that you found mapped very well to what operators wanted to check, from the as far as the formal techniques go. And then I guess the other side of that is, are there gaps? Like, are there things that the operators really wanted to check that just don't map quite as well to the formal techniques? Or how do you see that?
Yeah, that's a great question. It's potentially a big and interesting question. So so things that map well. So the basic thing we're doing in data plane verification is modeling how data is going to flow through the network, all possible ways data can flow through the network. So reachability properties are of course one. So there are security properties, like, for example, taking some examples from the Microsoft work, you have a cloud data center. Can my customer's VMs access my SDN controllers? They shouldn't be able to reach the control network or the management network. Are my customer VMs actually able to reach the other customer VMs that they're supposed to reach, right? So some of these reachability properties, that would be the most basic ones. But then you can certainly go beyond that, even just within stock data plane verification, because you're modeling how data can flow through. So you can ask questions like, are there any unusually long paths in the network? Are there loops in the network? Are there inconsistencies in data flow? So, for example, take two routers or two backup routes, two kind of components of the system that should have similar properties. And do they actually have similar properties? Do they, if one of my paths from one of my core routers flows through a firewall and the other one doesn't flow through a firewall for a specific kind of traffic, that might be something suspicious that I want to look at, right? So those are a few examples of understanding overall how data flows through the network, and I think it goes beyond just reachability, like, do you terminate at the right destination, to what happens in between, right? And looking across multiple paths and seeing if there are consistency issues and so on. So another example of that might be there's traffic that's supposed to remain localized in one region. Does it flow outside of that region? And that could be a performance issue. It could be a security issue as well. Okay, now what doesn't fit so well in there? And there are some interesting areas, and some of them are becoming really fascinating areas of research now. One area that I think doesn't fit so well within the published work on network verification is that's a real active need in industry is performance problems. So there's some performance blip in an application experienced by a user. Why did that happen, and where? Is it the network's fault? Is it where in the network, right? And it can be something that's very dynamic, something that could be caused by many different system components, not just the data plane forwarding layer, but it could be involved, right? So how that fits into verification is an interesting question. And then another direction I think that's pretty fascinating is not so much on the side of what question you ask, but what you're asking it about. That is, what of the network are you trying to model? And where the research work began was sort of forwarding properties, routing, and IP layer 2 through layer 4 forwarding properties of the network. But now imagine that we're getting more and more towards network functions incorporated into the models. So as you move in that direction, you're taking steps that move more and more towards. It starts looking more like verification of general purpose software, right? Not necessarily all the way in that direction, but you're taking steps in that direction as you get, as we move towards this trend of network functions being viewed as part of the network. And so there's some research that's starting to push in that direction now. And an example would be Katerina Argyriki's work on verifying software router implementations, where you're actually looking at she's looking at code implementing the a software data plane. Another example is Scott Schenker's student Arujit Panda is leading this work on verifying properties of that are kind of more stateful in the network that incorporate data plane functions. So those are two directions where I think this area of verification that's kind of more on the forefront of the research.
What kind of, I'm glad you brought up the network function stuff. I was going to ask, actually. So what kind of, I mean, I think you're right. It seems like as you sort of get towards placing these functions in the network, you get to sort of almost general purpose software verification. I mean, in that work that you mentioned, are there limitations that people are, like constraints that people are placing on what those functions can do that make the verification problems more tractable? Or I mean, what do you think are the sort of limitations there, or what do you think are sort of what's achievable actually?
Well, I think that's really very much an open question of what is achievable, because you can imagine pushing incrementally more and more in that direction. I think I'm not going to talk too much in detail about those specific projects, just so I don't say anything that's incorrect. But I think there are, for example, the paper that I had in mind on software data plane verification focuses on a single box at a time, right? Which is I think a very cool achievement even there, right? So I think as you do more and more stateful processing, more and more intelligent processing, and then moving towards verifying the actual SDN control programs themselves, which is another direction that's being pushed on. That's that gets really fascinating. I think it's I don't want to say what we can't do, because then I'll be surprised when someone does it.
No, definitely. So just a little bit more about your own work too, like on the research front. Like you focused a lot on checking properties of the data plane, snapshots, and things like that. And you kind of mentioned, for example, performance being a gap that's yet to be filled. But I wonder also, you can check the data plane snapshot with a formal approach. And I think in the course too, I talk about header space analysis,
right.
which
Right.
the data plane properties as well. But I think one thing that's not immediately apparent there is actually a couple things. One is like the control plane had to basically do something to put the data plane state there.
Yeah.
And if your formal verification is wrong, you might actually want to know, well, what happened. What happened that caused it to be wrong? Like, what's wrong with my control program? And so what's going on? And what are your thoughts on that? Actually, I mean, what are kind of the sort of limits of the analysis of data plane snapshots, and what's going on, if anything, in kind of control plane verification, and particularly as it seems like you can't do that in isolation either, because you mentioned Katerina's work on verifying software router implementation. That seems related to this a little bit. But what's going on in sort of what are kind of the limitations of data plane snapshot verification, and are people yet looking at how that ties to control plane checks and things like that?
Yeah, so I'm glad you're asking, because that kind of puts the approach in context, because the name that this approach is taking, data plane verification, is complementary to control plane verification. And there was earlier work, in fact, for example, your work on verifying BGP configurations from what I think 10 years ago now, can tell you, all right, is this configuration correct in at least some aspects before you push it out? And I think that's complementary to the approach that we took of that's pushing in the direction of how do we see as close as possible to what's really happening in the network and get the maximum confidence. And these are complementary, right? Because if you even if you're sure that a config is right, it's going to be processed through the you hand it off to the control software, which then runs distributed protocols, and is itself very complex, and maybe you're not modeling what it's doing correctly, or there's some bug even within that software, right? Or the config just maybe it's something simple. The config doesn't get pushed out to the device correctly. There's this trade-off between checking the configs versus checking something closer to what's really happening. So you'd like to get the best of both worlds, which is
I was going to say, is there a way to do both,
right.
obviously you can do both in isolation, but I don't know if that gets you.
Can you both check the configs before they run and also see something that's very confident about the live running behavior? So
yeah, and I guess to complement that, could you look at your data plane snapshots, and if you see something that violates a property there, can you go back to your control plane and figure out maybe what caused it?
Right. Yeah, those are really interesting questions. I think one way to do this is through simulating the control behavior, right? And so this is kind of an intermediate point. It's interesting, right? So you can simulate control behavior and then hand that off to a data plane verifier to get a very confident statement about what was the result of that particular control plane behavior, right? So maybe, for example, you simulate some link failure scenarios. What's going to happen if I have an outage? And then if I have an outage, is my control software going to behave correctly and actually produce paths that data plane behavior that has the correct forwarding properties, the correct multipath, the correct reliability, and so on. So you can kind of do a hybrid there, and this is an approach. So another paper from Microsoft Research recently. The name of that project is Batfish, where they're taking this approach, where they're actually saying, all right, we want, in fact, to understand the configs. So we're going to build a piece of software that can translate the configs through, I would call it a kind of simulation, can translate the configs down to data plane state and then run a data plane verifier on that, right? So this kind of two-step process. And then you can do the trace back of, okay, what was the cause of this behavior? And there's some other ways to do that without doing a full simulation. But that's one general approach to link the configuration root cause with the data plane, which is the ultimate forwarding behavior, what's happening to the live traffic that you care about. Now, this is interesting actually within the context of SDN, because in SDN you can do this more easily, right? There's a defined behavior for what the OpenFlow protocol, for example, is supposed to do.
Yeah, great point. Yeah. Otherwise, you've got to infer like what these messy control plane protocols are doing.
Right. You can. It's basically much easier to simulate your control software because you don't have to simulate it. You can just run it directly.
Right.
And have your and you may have talked about some of these advantages in your class already, and your students are using Mininet,
yep.
Right? Where you can take the same live control software configurations and control software, exact same code, and run it live, but in a emulated environment. And then you can imagine doing data plane verification within that environment.
Right, exactly. That's one of the points that I raised about Mininet is like one of the interesting things I think from an operational perspective is you can run something in an emulated environment, and your control plane could be exactly the same code as what you're going to deploy on real switches.
That's right. Yeah, so you can do a kind of unit testing or integration testing of networks in this way.
Yeah, that seems like a good way to kind of do some amount of checking in advance. I guess that's another kind of question I had for you was, what's your sense of like what's possible to do kind of ahead of time or in advance as opposed to at runtime? I mean, it seems like the data plane snapshot stuff actually now, per what we were just talking about, you could do a lot of that data plane snapshot checking, or some of it you could do in advance, right? You could sort of run something in Mininet, right? See what the data plane state is in your emulated network, and then run your data plane verification or your formal checks on a data plane in an emulated environment. Like, how much of that do you think applies to sort of check things in advance versus like, are you kind of, do you think the more appropriate approach is to focus on the runtime, if you will, and like really pull the data plane state off of switches to do the verification?
I mean, I think if I were running a network, I would want to do both.
Right.
I would. So
actually, I mean, this is. I haven't seen too many people doing both, so or at least I'm not aware of it. Maybe you know a bit more.
Well, no, I don't disagree with you. I think that the ability to to really almost deploy your control software, but in this emulated environment first. This is something that this is one of the big advantages of SDN, right? It makes that easier. The other, another project I'd mention is that lets you do that to some extent is Cisco's Viral project, VIRL, where you can run an emulated network effectively. So it's not necessarily tied to, and you could say OpNet is trying to do a similar thing, although it's not quite emulation, it's simulation. But yeah, I think the ability to emulate, all right, I want to get something that's very close to what's going to happen in reality and test that up front. Just like when I'm building a big software project, if I check in code, it's got to be tested first, right? It's going to run through unit tests and integration tests before it gets pushed out. Yeah. Even before it gets pushed out to other developers, let alone pushed out to deployment. That's a great
analogy. How far do you think we are from like a unit test for network config, or what do you think that would look like even? I mean, it sort of seems like we're talking about maybe there's something, someone writes a piece of control software and they run it, a unit test and emulation, and then something like that. I mean, how do you think we're close to something like that?
Well, I mean, I guess I think that's where we want to go, and I think we are, there's some good progress. I think probably the most challenging thing there is that we're actually very far from having such a clean SDN deployed environment that you really could emulate it all. And for the foreseeable future, most networks are not just SDN, and maybe they're not even just one kind of SDN, right? Maybe you will use different tools for different parts of the job, and it's going to be a pretty messy situation for the foreseeable future, for years certainly. Even though we can see the vision of where we're going to, where the behavior is well defined, the control software is separated from the simpler, lower level hardware functions. And with that separation, there's at least the possibility that if you take that approach and you push it further towards deployment and towards more complete deployment, then you really could get to that point of unit testing and integration testing in advance. But I think that's probably the biggest challenge is that we really don't have SDN everywhere.
Right. Yeah. The networks are messy enough that even they're just too tough to emulate as is. Actually, that was another sort of question I wanted to raise, or a topic I wanted to raise was kind of the nitty gritties of the real world, which is that, a lot of these things look nice and clean, particularly if you can assume SDNs, but then, you start looking at real networks and there's just a ton of legacy stuff, and anywhere from like, a little bit of SDN on the side to no SDN, or, oh yeah, we're looking at that, but we're kind of looking at our end of life cycles and things like that. So I'm wondering, what in your kind of, you mentioned the operational network that you worked on, and just in your exposure in general to the industry, how much are you kind of faced with people or operators who, what's the spectrum here? How many people are just sort of saying like, yeah, here's my legacy network and I just want you to check it, and in which case maybe something like the data plane snapshot stuff might be really apropos because the data plane is there. You can snag it independently of what's going on above. Versus like, I mean, how many people are saying, yeah, I'm half SDN, or
right,
or have you found people that are like, no, I really want to check my network and this stuff is just too hard, so I'm going to basically start migrating 100% to SDN. I mean, I think I've heard that from at least one operator I've talked to. So I'm wondering what you've heard.
Well, I think I think you're right that there's, I mean, really, traditional networks are pervasive, right? And, even if you have a few non-SDN boxes in your network, you don't know what they're going to do if you're assuming everything is OpenFlow, right? It's just, it wouldn't work. So, it's interesting, actually, because when we started this verification work, the first phase of the project, which was this, doing data plane verification offline, like grab a snapshot of the network and just spend some time checking it. We worked with an operational network, and that was completely traditional, right? It was a mix of about 5 different vendors with traditional routing and switching gear. And when we started, we weren't even really thinking about SDN at that point. And so I think that need has continued, and the second phase of the research projects in our group with myself and Matt Caesar and Ahmed Khurshid and others, then move towards the SDN world because there are exciting opportunities there, right? Because you have a much more well-defined model of what the hardware is doing. Makes it much easier to get data and model that data, and there's centralized control, right? So you can watch what the controller is doing. You can get incremental changes. You can verify incrementally, and then with the right algorithms. And this is another example of something that's kind of network specific, rather than off-the-shelf, formal methods techniques. You get these changes from, control changes from the SDN controller, and you can check just, in those incremental changes and push the latency down to milliseconds. So that's a pretty cool capability. It's something that you can imagine will even be part of SDN controllers in the future. So you verify before you push, the controller verifies before it pushes out any change to the network. So I think there's a lot of exciting capabilities there that you get from SDN, but at the same time, you can apply this concept to traditional networks, and it ends up being more work because there's a range of devices that you have to understand.
Right.
But there's a lot of need there just because most of the world and a lot of the complexity is in traditional gear.
Mm-hmm. Actually, you mentioned another thing too, which I thought to ask as well, is just sort of the ability to kind of do incremental testing. I mean, it seems sort of incredibly important. I think a lot of the formal verification stuff that I've read, at least, maybe of some newer work too, but a lot of it is comprehensive, right? You'll basically take the existing state and run some exhaustive checks or tests on that state. But I guess, I mean, certainly in software testing, there are these notions of, regression tests and behavioral regression and things like that. How much are you seeing like those ideas applied to verification? Because it seems like that could really help scaling as well. And also I think another thing there is operators may not have a lot of experience writing down sort of formal properties, but they might say, yeah, things are kind of like basically working right now. And I want to make sure that the next thing I do isn't going to break everything. And I don't really know what that means, but I know that things were kind of mostly okay right now. I mean, is there a notion of that? I mean, it's not really the way that formal methods folks typically think, but it seems to me like operationally that might be a useful thing.
Yeah, I agree. I think this is a little bit similar to the idea of consistency checking, which we used in our, one of our projects, and also is in the Microsoft work. You can think about consistency checking across devices in similar roles, like do my core routers all have the same behavior in some sense? Or you can think about it across time, right? Like, okay, so the behavior across time, if I change something, is the overall network behavior consistent across time, or did it change in the way that I expected? So just at a high level, I agree that that's useful. And then, so the second point you brought up is, I think, really fascinating. So it's the act of writing down what the network should be doing might be non-trivial.
Right, right.
And this is a really interesting area. So how do I express what the network should do? Right, and there's a lot of ways to attack this problem, and kind of higher level policies are one. Consistency is one, where I don't have to expressly say everything that happens. I can just say, tell me if there's anything weird.
Right, exactly. Yeah.
Right. But I think it's actually bigger than that. This is a question for SDN controllers as a whole. I mean, in my opinion, the biggest area of SDN that still remains to be resolved collectively by the community is great. Now we can program networks. How do we want to program them, right?
Yeah. So basically, all this
how do we express these?
Say how to do anything, right? So yeah.
Right. So how and we're talking about it in this discussion in terms of verifying. What do you want to check for? What do you want to verify? But it's really almost the same question as how do I tell the network what I want it to do? And so how do I represent those higher level goals or intent that the operator has? How do I express that? And do I use is there one controller that sort of handles the whole space of everything that I want to express, all the intents I want to express? How do I represent that conveniently? Or are there different kinds of controllers that are attacking, the killer app for wide area routing optimization might be different than the controller for the killer app of virtualized data centers, for example. Right. So I think that whole space of how do you express what the network should be doing is, I think it's fair to say that that's very unresolved in both the research community and in industry.
Interesting. Cool. Well, I think we touched on a ton of open areas. That's usually a question that I kind of ask to wrap up. I mean, you mentioned performance. We talked about sort of controlled data plane interaction. We just sort of talked about a whole other area of sort of policy expression and incremental kind of verification. Seems like there's a ton left to do. I mean, I guess before we finish, is there any other topics you think deserve attention that we didn't touch on that students or whoever watching might want to pay attention to?
Let's see. That's a good question.
Either in terms of like unsolved problems or maybe new technologies that are coming that might crack open some of the things that we talked about.
Well, I mean, I think it's a really interesting space overall that's evolving very quickly. There's, I think, one interesting area we touched on is how do you push verification towards richer and richer models of whether that's, software routers or network functions. What's the connection between this and other trends like white box switching or new kinds of forwarding hardware?
Right.
And how these affect our conception of what SDN is.
Mm-hmm. That's something we didn't really touch on at all, but I guess maybe next year or so, when the picture's more clear, we can talk again about all this. The students looked at programmable hardware like the core and stuff like that, and I think people are starting to think about verification there too. But what does that whole thing mean for data plane state verification? Is something that
that's a great question. You can imagine ways where it means that becomes more challenging because
more degrees of freedom.
Yeah, exactly. You can do more with the hardware. It again one more way in which it becomes more like general purpose software. You can also imagine that if we're moving towards a mindset where, hey, we really care about the network as being critical infrastructure, and we want to have confidence in what it does, if we take that mindset as we push in this direction, then there are opportunities too, because SDN and white box hardware, it lets us see what's going on much more easily than we could before, right? And that's the first thing you need. You need to understand, right? You need to be able to get access to the information and know what it means and what it's going to do. And I think that opportunity is there. So that means it's pretty exciting.
Cool. Well, thanks for your time today. I'm sure. I hope people sort of appreciate your perspective. I'm sure they will. It's been fun.
Sure. So thanks so much for the invitation. I really enjoyed it and enjoy the course. And I had a great time chatting.
Cool. Thanks, man. All right.
Okay. Thanks a lot. No. Bye-bye.
Bye.